All right, so here is the second half of that lecture. Thanks for being patient. Just putting parts out there. I like to chunk it up. Sometimes these videos can get long, and breaking it up into 2 or 3 parts usually makes it a little more digestible, but plenty of little details that we can get to down the road. So we left off with just kind of some basic ideas of the power rule and a few techniques and just recognizing notation. And so now one of the coolest things about antiderivatives actually is that you can apply a lot of the rules that we did for derivatives. So let me back up here a little bit. So here, this is something that you know, right? Deriving if y equals 5x to the 6th plus 2x, then dy dx is 30x to the 5th plus 2. Hopefully that's nice and easy for you. But what comes next then is, if I say let's integrate 30x to the 5th plus 2 dx, which is anti-derive, we're going backwards, then we will get 5x to the 6th plus 2x plus c. Do you realize when you take the derivative, we look at each piece separately to get the derivative? When we anti-derive, we do the same thing. So we really think about it in terms of, I'm anti-deriving that first chunk, 30x to the 5th, getting my add 1 to the power and divide by it. So that'd be to the 6th power and then divide by 6. And then here, this one's a new one. The integral of 2 is 2x, because we know the derivative of 2x is 2. It seems like when you integrate something that's just a constant, you just get that constant x. And of course there's a plus c at the end, because we could have derived anything with a plus c and it would have gone away. So think of, with integrating multiple terms, you just move one term to the next. All those that are separated by a plus or minus sign, you can take the separate antiderivative of. So you want to always find ways to separate antiderivatives between plus and minus signs, and it really does make your job easier. So for instance, let's get a couple basic rules under our belt, and then we'll look at derivatives with multiple parts. Because when you break these antiderivatives up, you'll run into certain things like this. So that one constant thing I was just telling you, the integral of 1, for instance, is x plus c, because the derivative of x plus c is just, the derivative of x plus 5 is just 1. So the derivative of x plus 7 is just 1, because the constant is 0. The derivative of anything, that one number like times x is that number that's multiplied to x. So let's be more general. If you have the integral of some constant is the constant times x plus c. Okay, so that's the big general rule. So if I have the integral of 5 dx, the antiderivative is 5x plus c. On we go. And again, you can always check it by deriving and going backward. The second, here's the power rule we already know. I'm just writing it a little differently. So if you have x to the n, it's add 1 to the power and then divide by it. But except, there is one exception when x is to the negative 1 power, because if you do add 1 to that power and divide by it, you're going to get x to the 0 on top over 0 on the bottom, and you cannot divide by 0. So there's this one exception. X to the negative 1 is a special case, so we want to look into that one. And there's another couple special cases out there, but that's the big one. Integral of 1 over x. You rewrite it as x to the negative 1. That's something that we're going to practice here in a minute in general, is how do you rewrite things so that they're in the power rule form, just like we did with derivatives. And if you do that one, that's a special case. You want to learn to recognize x to the negative 1 or 1 over x. You can't integrate except you know that it's the natural log of the absolute value of x. And those absolute values matter too. So that's one to memorize. And if we had time along the way, or maybe in Calc 2, you'll get a chance to see how or why that's the antiderivative of 1 over x. Okay, so negative exponents are definitely okay. It's not that they're bad, it's just that negative 1 is the naughty one. Anything else is okay. And well, again, we'll see an example of that here shortly. Okay, so instance, here's x to the negative 2, the antiderivative. If you add 1 to that power, be really literal about that. It's x to the negative 2 plus 1 over negative 2 plus 1. And then there's a plus c. Have to have that at the end. And you do simplify, so you end up with x to the negative 1 over negative 1. And keep going. All your exponent rules really come into play. If you remember, x to the negative 1 moves to the denominator. And so it's not that the negative 1 in the denominator flipped. I want you to be careful not to assume that's what happened. It's just we're really thinking of it as 1 over negative 1. And 1 over negative 1 is just negative 1. But this is the only thing that moves to the denominator is the x to the negative 1. So it becomes x to the positive 1 when you do flip it down there. So be careful on those assumptions. That negative 1, the denominator, really didn't flip. It's just 1 divided by negative 1 is negative 1. Okay. Here's another example. 5x to the negative third. The antiderive, the 5 stays. but you add 1 to the power, whatever it is, and divide by it. Okay, so this ends up being kind of a nice problem. Negative 3 plus 1 is 2. So remember your exponent, you're adding 1 to it, and you divide by that same number. So your exponent and the number you're dividing by have to match when you're anti-deriving with the power rule. It's a good way to check that you're on the right page. So I've got x to the negative 2, and then also I'm dividing by negative 2. And then a little simplifying on the end there. We can go further. So again, x to the negative 2 is 1 over x squared. So you can do that, and then, pull it together as negative 5 over 2x squared, etc. But just know all your rules of exponents are going to become important when you're doing power rule, which involves exponents and antiderivatives. Okay, so on the flip side here, so simplifying, you get into the power rule. So if you get something, and you're going to have to start recognizing that a lot of times you just try and rewrite your integral so that it is in the power rule form. I'm going to give you an example. So this isn't one that you need to simplify, but I want to give you a reason why it would be helpful. So let's do the antiderivative here. Each part of it, I'll antiderive. So sorry, this went a little bit fast there. But if you do 12x to the 5th, you add 1 to the power at 6, divide by 6. 6x is to the first, so you add 1 to that power, it's squared, and you divide by 2. And then plus c, of course. Then you simplify a little bit, 2x to the 6th minus 3x squared plus c is the antiderivative. If you want to check it, take the derivative of that. You should get what's in the integrand there. Now, what if I wrote this a little differently? Here is actually an equivalent integral. 12x to the 6th minus 6x squared over x is the same as the integral on top. So the thing is if you're dividing multiple terms by another term, we know algebraically we can split that up, and splitting up integrals into the sum and difference of different pieces is a really good idea. As often as you can split it up into plus and minuses is often a good idea. So you always want to look for those algebra techniques where you can split it into the sum or difference of parts. Then, when you do that, you get something more familiar, which is the integral we've already done up above. So look to simplify before you start your integral if that's possible. And one of the most popular is if you see something in the denominator, divide each term on top by that value. Okay. Fractions. So fractional exponents scare folks, but it's still a power rule issue. So here's a string of terms, an integral of all those together. And you want to be careful. That very first one, I want you to recognize that's actually going to be our natural log issue. That's x to the negative 1. So you want to start training your eyes to see that's the one you can't really do with any power rule. We just want to know, oh, that's that special one. That's going to be 4 ln of x, okay, when we antiderive that. But I'm going to leave that. I'll do it later, but I just want you to know I'm kind of keeping my eye on that. But the others are, write these in terms of powers. Make these power rules. So you may or may not remember all these exponent rules, but the thing is square roots are half powers. X to the 1/3 in the denominator is x to the negative 1/3 on top, and x squared of x is also x to the 1/2, or negative 1/2 on that last term. This is in power rule form, where you have some x to the nth. If you can get into that, that's a good thing, because we have a way of anti-deriving that. The first one, of course, is different, but every rest of those is just add 1 to the power and divide by it. And it looks complicated because there's fractions, but the rule doesn't change. Check this out. I'm still adding 1 to the power in each case and dividing by that number, adding 1 to the power and dividing by that number, adding 1 to the power and dividing by that number, etc. So this is a correct antiderivative, where I added 1 to each power and divided by it. I just have a little work to simplify it. It's accurate. It's all I really need if somebody says just execute it and get it done. But obviously there's a lot of reason to simplify these down. So here's the first stage in simplifying. If I take each of these, I'm just going to rewrite it real quick on this new page so you can see where I left off. And again, I know the videos go fast, but that's the beauty of videos. Pause and go back as necessary. And the thing is, as we simplify, we can do things like, if you're going to add fractions, you need common denominator. So clever forms of 1, like make it into 2 over 2 instead of 1, or 3 over 3, etc. Okay, so that's pretty consistent. And then when you add those fractions, then you can take and start, when you have fractions in your denominator, as we're starting to see here, then when you're dividing by a fraction, you multiply by the reciprocal. So you want to end up multiplying each of those fractions by the reciprocal. But this ends up being pretty common with fractional exponents. You're going to add 1 to the power and divide by it when anti-deriving, just like you did with any other number except negative 1. And when you divide by a fraction, just remember you'll end up multiplying by a reciprocal. And so the end up all cleaned up version, I think this is as clean as you'd ever need it to be, just involves I'd multiply by the reciprocal, and then I have fractional powers when I'm done. And if you want to check it, the derivative of what you see here will end up being the same as what our integrand was on the previous page. And that's the end of it. So just be careful. Again, x to the 1/2, maybe one other step might be calling that square root of x. But that's about it. That's our intro. That gets us off to a good start, and enough for you to be able to do some antiderivatives for the assignment, and it'll be due after the break, the Tuesday night after the break. They're not terribly difficult. Google all you can on just basic antiderivatives if you need help, but it's a lot of exponent work and just being able to use the power rule. We'll do more conceptual stuff on Monday when we get back, and happy Thanksgiving.